to try and find a compelling explanation for Kleiber's law.
They started by assuming three simple premises. The first premise is that the networks that distribute resources are space-filling, since they need to reach every cell in the body. The second premise is that the terminal units of those networks, the thinnest segments on the outer periphery of the delivery system, have the same width regardless of the size of the organism. That is, the outermost blood vessels that carry nutrients to an elephant's skin cells are about as thick as the ones in a mouse. The elephant just has many more of them. And the third premise is that over time, evolution has driven these transport networks toward an efficient design. So what should such a network look like? Well, intuitively, to get fuel from one place to another as efficiently as possible, you want the path to be as short as possible, so basically a straight line. But because fuel needs to reach every part of the body, you would also need many different paths. And as you go to larger and larger organisms, the networks inside need to reach a larger and larger volume. One way to do this is to stretch all the paths and match the growth of the animal. In this case, the volume of the animal should scale as these internal path lengths cubed. Or if we rearrange that, internal path length should scale as volume to the 1/3, just like the overall length of the animal does. But this design is incredibly wasteful. Take these two regions. The two vessels that are bringing blood here go through almost the same path in the body, and they only split up just before they reach their destinations. If instead we had just one vessel up to this point and split it only when the paths needed to diverge, we could serve the two regions using a lot less vessel material and a lot less blood to fill the vessels. Of course, you can extend this logic for all the blood vessels in the body, and you end up with a much more efficient design of branching blood vessels. But now we run into another issue, because each branching point provides an opportunity for some of the blood to bounce back, that is, reflect. If you have many reflections, that would mean it costs significantly more energy to pump blood around. So next, they argued that nature should favor structures that minimize reflections. And as it turns out, this happens if the cross-sectional area of the vessels stays the same before and after the branching. So if you've got a cross-sectional area of 2 centimeters squared for the main vessel, then each of the two branches need to have an area of 1 centimeter squared each, for large vessels at least. For smaller ones, daughter branches can be a bit thicker to allow blood to slow down and exchange resources with the tissue it's reaching. If you keep repeating this pattern across the network, you end up with this, a branching self-similar fractal. And if you look at the actual shape of the circulatory system, it has this geometry. So it seemed like they were onto something.
But how do you get from this to quarter-power scaling laws? Well, mathematician Felix Hausdorff discovered that self-similar fractals have an interesting property. Take a straight line segment. It's completely one-dimensional and not a fractal at all. Hausdorff assigned this line segment a value of 1.0. But now imagine adding a few bends. And more bends to those bends. If you keep doing this, the line becomes more and more fractal-like. Eventually, if you keep applying the right kind of contortions, that one-dimensional line segment fills up an entire region of the 2D plane. Hausdorff assigned these space-filling fractal curves a value of 2.0, corresponding to their dimensionality. The same ideas apply to a 2D surface.
So think about a piece of paper, right? Two-dimensional. All then the fractal network is doing is crumpling up that sheet of paper, and it effectively fills a ball of volume. So you can now describe that sheet of paper as a sphere instead of a two-dimensional sheet of paper.
Repeat the right pattern of folds at smaller and smaller scales, and a 2D surface fills more and more of a 3D volume. In the mathematical limit, it becomes space-filling, with a Hausdorff dimension of 3.0.
Biologically, well, what does that mean? That enables an organism for a given size to pack in more of these metabolic surface areas than would be expected. And it's because of this fractal-like structure that enables you then to pack in and have all of these folds and convolutions and on top of each other, to pack in an enormous amount of membrane surfaces.
As a result, the Hausdorff dimension of the surface of the circulatory system is roughly 3, meaning its surface area doesn't scale as its length squared, but its length cubed. And since the metabolic rate hinges on how fast resources can be exchanged across the surface area, well, it must also scale like length cubed.
But remember, West, Brown, and Enquist wanted to explain Kleiber's law, so they needed to know how metabolic rate scales with mass. Since every cell needs to be served by the network, this means that the volume around the network should be proportional to the animal's mass. And since volume is just surface area times length, and surface area is proportional to length cubed, that means both volume and mass must be proportional to length to the 4th. which can be rewritten to show that length is proportional to mass raised to the 1/4. And if you plug that into the equation for the metabolic rate, you find that the metabolic rate must be proportional to mass to the 3/4. Exactly as Max Kleiber had found. West, Brown, and Enquist published their work in 1997, and it soon came to be known as WBE theory, after their initials.
And the theory is quite rigid. It makes very specific predictions. This is good science, okay? This is sticking your neck out, and it's an incredibly beautiful theory.
Take a look at this table from Geoffrey West's book. These are the scaling exponents WBE theory predicts, including many that are not multiples of 1/4, but all follow from the same theory. For example, the radius of an animal's aorta should scale with its mass to the 3/8, or 0.375, and the area of its lungs should scale with mass to the 11/12, or about 0.92. In total, this chart makes 26 different predictions. Now, these are the observed data. Radius of the aorta, 0.36. Lung area, 0.95.
That's the really shocking thing about what they did. They had a table with something like, 20 or 30 predictions of exotic exponents, and that's what you really see in the data. So this one theory accounts not only for the 3/4 power of metabolism, but for literally dozens of other things that biologists have measured.
Some of the scaling laws are easy to explain once you've got the 3/4 law for metabolism. Take a mammal's heart rate, for instance. Heart rate is equal to the blood flow rate over the amount or volume of blood in every beat. The volume of blood per beat has been found to scale in direct proportion to an animal's mass, so that's just m. And the blood flow rate? Well, remember that metabolism is all about how nutrients get distributed around the body. So most biologists agree metabolic rate and blood flow rate are directly proportional to one another. So heart rate should scale as metabolic rate over mass. Swapping in the scaling law Kleiber had found, that gives us m to the minus 1/4. Meaning bigger animals should have slower heartbeats than smaller ones. And this is exactly what we observe in nature. The world's smallest mammal, the Etruscan shrew, has an extraordinary heart rate of 1,200 beats per minute. That's 20 beats per second. Whereas the biggest land mammal, the African bush elephant, has a typical heart rate of only 30 beats per minute. And we can do something similar for lifespan. One of the leading theories is that an animal's lifespan is based on the accumulation of metabolic damage. That is, as each chunk of tissue in an organism processes nutrients over time, this causes damage to accumulate. And that, over time, causes the animal to die. So the rate at which an animal accumulates damage is its metabolic rate per unit of mass, and its lifespan should be the inverse of that rate. If damage accumulates faster, it dies sooner. If it accumulates slower, it lives longer. So lifespan is proportional to m over b, or substituting in Kleiber's law, m to the 1/4. So lifespan should increase with mass, and you do see this in nature.